This video gives an overview of mass spectrometry. Mass spectrometry, or mass spec for short, also just abbreviated MS, is used to determine the molar mass and formula for a compound. The process involves vaporizing and then ionizing a compound, which then undergoes fragmentation. And then in the instrument, the masses of the ions are detected and graphed. This diagram shows a representative illustration of a mass spec instrument. In this, a sample is inserted at the inlet, and the sample is vaporized, and then it's bombarded by electrons and ionized. So the electrons are produced by a heated filament such as a tungsten filament. These electrons that are bombarding the molecules are energetic enough that they will kick off an electron from the organic molecule, and as a result, a positive ion is formed. This ion is called the molecular ion, or sometimes it's called the parent ion. These ions are very unstable, and some of them will break up into smaller pieces known as fragments. The ions leave this ionizing chamber and are accelerated through the instruments using a series of slits. Then they enter a magnetic field, which is produced by the magnet shown here. And based on their mass to charge ratio, when these enter the magnetic field, they will be deflected to different angles, with lighter masses being deflected to a greater degree than heavier masses. By varying the magnetic field, we can sort these ions and direct one mass to charge ion through this slit into the detector where it's detected. There are a large variety of methods for ionizing molecules, but the most common is electron impact, which is what I was describing in the last slide. So in this, you bombard a sample with an electron beam, and as a result, an electron is ejected from the molecule. So for example, if you have this representative organic molecule, you would bombard it with a beam of electrons, and then an electron would be ejected to form a radical cation. So you've lost one electron, which is why it's now a radical, and if you lose an electron, you're going to form a positive species, which is why it's a cation. Now these can be tricky to draw because they defy our common understanding up to this point of what Lewis structures look like. So you can draw it like I've shown here, but sometimes it's also drawn like the typical structure with the brackets and a dot plus on the outside indicating it's a radical cation, so it doesn't really look like that. The mass of the radical cation that's initially formed is the same as the parent compound because the mass of an electron is very, very tiny, so it's essentially negligible. Therefore, if we can determine the mass of the radical cation, we can determine the mass of our compound. If this radical cation remains intact by the time it gets to the detector, it's known as the molecular ion or the parent ion. This is really useful because if we know the molecular ion mass, we know the mass of our compound. Now, as you might imagine, a radical cation is pretty unstable, so it will typically fragment and break apart into smaller pieces. So in this example, this radical cation breaks apart into a radical and a carbocation. The ions that are deflected by the magnetic field are deflected according to their mass to charge ratio. Therefore, if there is no charge, they will not be detected. So lighter fragments are deflected to a greater degree than heavier fragments. In the spectrum that we get, the output from this experiment, we have a graph where on the x-axis is the mass to charge ratio, and the y-axis we have the relative abundance. So this is going to give us a series of peaks for each ion that is detected. There are a couple terms that we use. One is the base peak. The base peak is defined as the tallest peak in the spectrum. Therefore, it's the most abundant fragment. Now here we see that the base peak is at a value of 16, which is the mass of methane. So in this case, the base peak is also the molecular ion peak. These other peaks shown here would be fragments. And I'll talk about what this peak is to the right of the molecular ion peak in a minute. So those other peaks in that spectrum that we just looked at represent fragments. So this molecular ion can lose hydrogens to give a mass-to-charge ratio of 12, 13, and 14. Mass spec is a relatively sensitive analytical method, and it's used in a variety of contexts. It's used in drug discovery, it's used in biotech to do analysis of macromolecules, it's used in the clinical setting, it's used in the environmental setting to do drug testing, to evaluate water quality. It can be used in forensics for explosive detection and in geological fields, for example, to evaluate oil composition. In airport security, specialized mass specs are used to detect explosives on the surface of luggage. Let's look at this example mass spec for benzene. So over here at the right, this would be 75, 76, 77, 78, we have the tallest peak, which is by definition our base peak. It's our most abundant peak. This also corresponds to the mass of benzene. 6 carbons times 12 AMUs per carbon plus 6 hydrogens equals 78. All of these other peaks correspond to fragments of benzene. Now with benzene, the base peak was the molecular ion peak, but that's often not the case. So if we look at pentane, the mass spectrum shows that the base peak is at 43. That is not the mass for pentane. So indeed, the molecular ion peak is way over here, and it's quite small. So this shows you that the parent ion for pentane fragments quite easily. The first step in analyzing a mass spec is to identify the molecular ion peak, because that's going to tell you the molar mass of the compound. This is one of the key pieces of information you can get from mass spec. Also, you should know that an odd-massed molecular ion peak generally means that there's an odd number of nitrogen atoms. An even-massed molecular ion peak generally indicates an absence or an even number of nitrogen atoms. So for example, pentane has a molecular weight of 72, which is an even number. However, if we replace one of the carbons with a single nitrogen, we get an odd number for the molecular weight. However, if we add 2 nitrogens, we're back to an even number. Now I mentioned that there's this little teeny peak to the right of the molecular ion peak. So what is that from? This is called the M+1 peak. The M+1 peak results from the presence of the isotope carbon-13 in your sample. So remember that carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14. The weight you see on the periodic table is an average of those isotopes taking into account their natural abundance. However, when we're thinking about a mass spec, that mass spec is going to detect the exact mass of the particular carbons in your sample. So a particular carbon is going to be either carbon-12 or carbon-13. There's so few carbon-14 atoms, we don't have to worry about it. So about 1% of all carbon atoms are carbon-13. So as a result, whenever you have a carbon-containing molecule, you're going to have a peak to the right of the molecular ion that is 1 atomic mass unit higher than the parent ion peak. And that's because 1% of methane molecules that pass through the instrument will have a carbon-13 atom, not a carbon-12 atom. Now, if you increase the number of carbons in your molecule, there's more chances that those carbons could be carbon-13 atoms versus carbon-12 atoms. And this is just a result of statistics. So as the number of carbons increase, the height, the relative abundance of that M+1 peak will also increase. And we can use that to our advantage because we can compare the height of the molecular ion peak and the M+1 peak to determine how many carbons are in the molecule, which will help us figure out the formula. And we're going to do some exercises in class on this. Now, other types of atoms also have isotopes. For example, chlorine has two abundant isotopes, chlorine-35 and chlorine-37. The chlorine-35 is the more abundant isotope. It's about 76% abundant, and the chlorine-37 is about 24% abundant. So the ratio of those two numbers is about 3 to 1. So if you have a compound that contains a chlorine atom, such as chlorobenzene shown here, you're going to have the molecular ion peak shown here, but you're also going to have an M+2 peak shown here. And then each of those peaks has a small peak to the right of it. So this is your molecular ion. That's with the compound having the chlorine-35 atom. And to the right of that is the M+1 peak. So that would be the chlorobenzene where you have the chlorine-35 and one of the carbon atoms is a carbon-13. Then the M+2 results from the chlorobenzene where the chlorine atom is chlorine-37. And then the peak to the right of that, which would be the M+3 peak, is the chlorobenzene where you have chlorine-37 and one of the carbons is a carbon-13. Bromine also has two isotopes like chlorine, but their relative abundance is 51% for the bromine-79 isotope and 49% for the bromine-81 isotope. That means that they are about in a 1-to-1 ratio. So if we look at this example of bromobenzene, we see the molecular ion peak here, and we see an M+2 peak. So notice that the approximate ratio of the heights of those two peaks, the M and the M+2, is about 1-to-1. So that is an indicator that you have bromine in the molecule. So the molecular ion peak is formed if all of the carbons in the bromobenzene are carbon-12 and the bromine is bromine-79. The M+1 peak here would be the bromobenzene with bromine-79 and with one of the carbons as carbon-13. And then the M+2 peak would be bromobenzene where the bromine is bromine-81, all the carbons are carbon-12, and then this M+3 peak here is with the bromine-81 isotope and one of the carbons being a carbon-13. So if you just want to check my math, you can add up all of the atoms individually and verify that they do equal the masses shown. So in addition to the molecular ion peak and M+2 peaks, we can also analyze fragments. So if we consider pentane, this would be a representation of the molecular ion of pentane. So it's lost one electron, therefore it has a positive charge and it is a radical. So if it loses a methyl radical, we would get this fragment here, which would be equal to the parent ion mass minus 15 mass units. If it lost an ethyl radical, we would get this cation, which is the parent ion mass minus 29 mass units for ethyl. If we lost a propyl group, we would have the ethyl cation left, which is the mass of the parent minus 43. So this has a mass of 43. And then if we lost everything but a methyl, we'd get this fragment, which would be M minus 57. Now remember, the mass spec instrument only detects charged fragments, so these neutral radical fragments would not be detected. So if we look at the mass spec fragmentation pattern for pentane, here we see the fragment resulting from the loss of a methyl group. This is the fragment from the loss of an ethyl. And this is the fragment from the loss of a propyl, and this would be the fragment from the loss of the butyl. And then the additional lines around each of those ions are the result of further fragmentation, specifically the loss of hydrogen atoms. When looking at all of the possible fragmentations, the one that is the most abundant fragment will also coincide with the most stable cation. So if we look at this molecular ion, it will fragment to give a tertiary carbocation and a primary radical. So a tertiary carbocation is more stable than a secondary or a primary, which is why this is the most abundant fragment seen. Now you may be wondering, how would you draw a mechanism for this to illustrate the electron flow? So we'd want to redraw this where we're going to remove the electron from the sigma bond that ends up being broken. And so I'm going to draw a dashed bond to indicate that there's only one electron in that bond. And then I'm going to use a fishhook arrow and show that one electron going to the carbon, which would then leave behind this carbocation and this radical fragment. So drawing these radical species and their fragmentations can be a little bit tricky and different from the mechanisms that you're used to drawing. Alcohols undergo two main types of fragmentation, alpha cleavage and dehydration. So if we look at a typical alcohol, this would be the molecular ion. So if you have a compound that has a lone pair, the electron that is ejected in the ionization step will come from one of the lone pairs. Also, if you have a molecule with a pi bond, the electron that's ejected will be removed from the pi bond. So there's an order of ease in which electrons are removed. The easiest place to take an electron from is a lone pair, followed by a pi bond, followed by a sigma bond. So in this case with an alcohol, we've removed an electron from a lone pair on the oxygen, which is why there's this third electron here, and we don't have two full lone pairs. So in the alpha cleavage, that one electron will pair up with an electron from the adjacent sigma bond, which will also cleave, and that gives you this resonance stabilized carbocation and a neutral radical species. In addition, you can lose a molecule of water, H2O, which is why this is called dehydration, to give an alkene product. Amines also undergo alpha cleavage in the same way that alcohols did, and carbonyls undergo something called the McLafferty rearrangement, shown here. So here, one of the electrons, the unpaired electron on the oxygen, pairs up with an electron from that CH bond, and then the other electron forms a double bond between the beta and gamma carbons, and then this final electron moves on to the alpha carbon. So as a result, you get an alkene, and you also get this radical cation species. This table shows the common fragments lost in mass spec. So 15 corresponds to a methyl radical, 15 is CH3, a carbon plus 3 H's, 29 is ethyl, 43 is propyl, 57 is butyl, 18 indicates that you lost water, and M minus X, where X is an even number, is indicative of a McLafferty rearrangement. In addition to mass spec, there is high resolution mass spec, which allows you to measure the mass to charge ratio up to 4 decimal places. So masses are not whole numbers. So for one proton, it's 1.0073 AMU. And while one carbon-12 atom is exactly 12.0000 AMU, that's just because the entire AMU scale is based on the mass of carbon-12. So all atoms other than carbon-12 will have a difference in their AMU masses out at those decimal places, and those can be discerned if you use a high-resolution mass spec. So for example, if we look at these two compounds, this is cyclopentanone and this is cyclohexane. If we only are looking at the approximate weight, they would both be 84 AMU. However, they are clearly different compounds. So if we instead used a high-res mass spec, we would get weights out to the 4th decimal place, and based on that, we could discern whether we had cyclopentanone or whether we had cyclohexane. There are also other types of mass spec that are better for large biomolecules, and one type uses electrospray ionization instead of electron bombardment. And in this, a high voltage needle sprays a liquid solution of an analyte into a vacuum, causing ionization. This is considered a soft technique because the molecular ions stay intact and generally don't fragment. And this is very useful for large molecules that would otherwise just give really ridiculously complex fragmentation patterns that would be very difficult to get any useful information from. Now test your knowledge. Based on this video, do you know which of the following compounds will have an odd mass to charge value for the molecular ion? Look at this mass spectrum. Can you tell me what is the molecular ion peak? And based on the spectrum, what halogen must be present? So is there chlorine, bromine, fluorine, or iodine present? Now here is a mass spectrum for 2-methylbutane. This is the molecular ion 72. Notice that there is a peak here at 57. What fragment was lost to form the peak at 57? So it helps to do a little math and figure out the difference between the numbers 57 and 72. And that's it for this video. Thank you.